So good morning, everyone. My name is Francisco Monteiro, and today what I bring you here, it's an overview of my PhD topic so far on cryogenic fluid storage. And I like to call this presentation From Sloshing Dynamics to Active Pressure Management, as a big part of my PhD so far has focused on sloshing characterization, and now we are taking the first steps towards digital twinning and control. So, thermal management of cryogenic tanks. Overall, the landscape of our problem is quite simple. We have a tank and we want to store a liquid within it. Nevertheless, the key challenge here is that the liquids that we are working with are only liquids at extremely low temperatures. May we take the good example of liquid hydrogen, stored at about minus 253 degrees. So, as you can imagine, regardless of the environment that we place these tanks in, usually we have extreme thermal amplitudes between the outside and the internal contents, which leads to parasitic heat fluxes that penetrate the tank shells. These parasitic heat fluxes lead to buoyancy-driven flows at the walls that transport this warmer liquid to close to the interface. This warmer liquid exchanges with the gas, building up superheated vapor with pressure buildup associated to this process, and thus the settlement of a thermal non-equilibrium condition, characterized by this thermal stratification that we see in this schematic. Hot vapor on top, a saturated gas-liquid interface, and a subcooled liquid at the bottom. Besides that, until now, we are considering the simplified assumption that the tanks are under static conditions. This is rarely the case. Most of the times, they are storing propellants for spacecraft, liquid hydrogen, liquid oxygen, both used for spacecraft propulsion for decades now, and the prospect of using liquid hydrogen for aviation. So as you can imagine, we have multiple amplitudes and multiple frequencies injected into these tanks, which lead to sloshing. Sloshing being the free surface motion within these partially filled tanks. Obviously, this has a dynamical impact, as it shifts the center of mass, but focusing on our thermal management problem, it has a thermodynamic impact, as it mixes the subcooled liquid with the hot vapor and enhances exchanges with the walls. So, you see, we started with a rather simplified landscape, and right now we have a very complex thermodynamic environment in our hands. So it is clear that the way forward is through active thermodynamic control solutions, and that's precisely the key objective of this thesis, where we want to measure, characterize, twin, control, and actuate in such a way that we can optimize the pressure management in these storage tanks. So overall, what you see here, it's the menu of the PhD and also the menu of the presentation of today. And starting briefly by overviewing our first efforts focusing on space applications and sloshing, here our objective was to characterize sloshing-induced heat and mass transfer across gravity regimes. To do this, we did experiments on ground, gravity-dominated, and also in a parabolic flight, where we have a gravity step reduction in like profile from hypergravity conditions to microgravity and again to hypergravity. In the interest of time, I'll just mention briefly the experiments we did here in the parabolic flight. You see here the experimental setup that we developed, and our key objective was to answer to these two research questions. First, we wanted to know if there's a coupling between the thermal conditions and the sloshing dynamics. So that's why we carried on board two small-scale tanks, one isothermal, no thermal gradients, and the other non-isothermal, such that we could see if this thermal conditioning of the tank and thus of the vapor and the liquid would have an impact in the dynamics. And at last, we wanted to see thermodynamically wise, how would our pressure evolve, as this was the first time a parabolic flight was used for this. Overall, I just bring here a couple of snapshots. There are also very cool GIF videos that I could show afterwards, but this is a PDF file. So we start with both tanks, isothermal, non-isothermal, under hyper-G conditions. Then, as the gravity goes down, the liquid starts to climb up the walls, and after some time of mixing, it reaches some sort of equilibrium, where we no longer have much motion. And the cool part is that we see here is that in a non-isothermal cell, once the liquid goes partially in contact with the superheated part of the tank, where before we had the hot vapor initially, when we had the liquid at the bottom of the tank, we have boiling being triggered, which to some extent modifies a bit the dynamics, but the macro dynamics still is there. We are just to some extent splitting the single interface into multiple interfaces. As you can imagine, this also led to very strong pressure fluctuations in our signal, and this was a work that we published already last year in Experiments in Thermal and Fluid Science, where we did a complete analysis of this thermodynamic evolution in a gravity step reduction. Now, towards aviation applications. And here, our objective still was the same. We wanted to characterize sloshing, but now we change our system. While for space applications, we are concerned with vertical upright cylinders, in aviation applications, we are now concerned with horizontal cylinders. Besides that, here, our focus was vertical sloshing, which has been a concern of the industry, yet is very underexplored, and there's not much information in the literature at the moment. So what we did, we grabbed this small-scale tank that you see here, we strapped it to our Shakespeare sloshing table, and we sloshed it. We sloshed it quite a lot. Where our research question, and we wanted to answer to this, was which sort of sloshing regimes arise in this geometry under vertical accelerations. To do this, we developed the image-based pipeline. Obviously, it started with a bit of image pre-processing, as the camera was also strapped to the shaking table, so we had to remove some vibrations. Then, to simplify our analysis, we deployed MPOD to some extent to compress our data, and such that we could leverage only the dominant spatial structures and associated temporal coefficients. And then we get to step 3, the critical step of the methodology, which we called prototype-based data clustering. Here, the idea is that we built a library. Into this library, we put a couple of the spatial structures that dominate the dynamics that we could see. And then into this library, we project all the other test cases that we did not see. So we had no idea what sort of sloshing dynamics we had here. Based on this projection, by the end of the pipeline, what we have is an energy signature that tells us what is the similarity of these test cases relative to this prototype library. Based on this, then we did some clustering such that we moved from unlabeled data to labeled data. And at the end of this step, what we have is that a given sloshing point with a given forcing amplitude and a given forcing frequency belongs to cluster K. Then, based on this clustered data, now we have labeled points. We did a support vector machine such that we could draw continuous boundaries and build a dimensionless map that allow us to know for our forcing frequency and forcing amplitude which sort of sloshing regimes would arise in a given region. This was also work that we presented preliminarily last year at EUCAS, and right now it's under review at PRF. Now, to conclude on the steps that we just start working now with the flavor of digital twinning and control, at the moment, our idea still is to build this complete pipeline, which is basically towards model-based control. We are still working on the part of developing the 0D models to characterize our storage tanks. For today, framing into the environments that we are developing, here we have 2 experiments, one non-cryogenic and the other cryogenic. On what concerns the cool one, which is the cryogenic facility we are developing, we are moving from the small-scale tanks that we had before that were close to 1 liter to this large tank which is close to 130 liters for liquid nitrogen, mostly because we need to have enough space for hardware integration of our actuators. And here, the idea is that we have a second volume coupled to the tank, which we called it the vacuum chamber, where we are developing a thermodynamic vent system, which basically consists of open refrigeration loop, where one stream of liquid is expanded, it does at a lower temperature. The other one circulates in a closed loop by means of a pump. We cool it down in a heat exchanger. We re-inject it through the bottom of the tank, mix the liquid, remove the thermostratification, control the pressure over time by guaranteeing that we can offset the parasitic heat ingress into the tank. The cool part about this is that we developed in such a way that we can rotate it, such that we can do this study, focus on space applications, but also on aviation applications. And as you see in the photos, at the moment we finalize basically the commissioning. We missed the step of aerogel insulation of the tank, and hopefully by the end of this month, we'll be able to do the first chill down to see if the tank either works or hopefully does not explode. So in terms of valorization perspective, besides publications and conferences, we had a lot of fun, at least me this year, by helping out in the digital twinning, a simulation and control course at VKI, where we tortured a bit the students with Arduino, Raspberry, National Instruments, and all the sort of sensors you can think of. And at the moment, we are working towards maybe spinning off this research idea of twinning and control under the ERC of Professor Miguel towards maybe something. So if someone has experience here with spin-offs, I would love to grab a coffee with one of you. With this in mind, thanks a lot for your attention, and I'm open for questions. Thank you.